Okay, probability generating function for the geometric distribution. So we've done this quite recently, but quick recap. So if x is the number of tries to achieve the first success and the probability of success is a constant, then x is geometrically distributed. Probability of success is p. And then the probability that you get your first success on your x, I can't say that, x trial, is you would have failed to get a success x minus 1 times, and then you'll get your first success on the x trial. Stop trying to say it. And then q is equal to 1 minus p. So that's your probability that x equals x. I'm going to go over example 5 from your. This one is in your book. It just saves me having to write out the example, in all honesty. That gives us something to work with. But this is, yeah, it's in your textbook if you want it. So we've got a fair tetrahedral dice. It's rolled until the dice shows a 4. Discrete random variable x represents number of rolls up to including the first 4. And we want to show from first principles that the probability generating function for x is given by a quarter t over 1 minus 3/4 t. So x is geometric a quarter. And I'm going to write this out as a probability distribution to start with, like we did with the other ones. I think it just makes it nice and clear. And so in the geometric, x starts at 1. So you need to have a trial to have a success on that trial. And it's actually an infinite distribution. So the probability of getting your first success on your first trial is a quarter, and then 3/4 times a quarter, and then 3/4 squared times a quarter, 3/4 cubed, that's probably enough really, times a quarter, etc. And then the probability generating function for x. I didn't write this on the other two proofs, and after I thought I possibly should have done. But anyway, it's a sum between t equals 1 and infinity. Obviously for binomial and Poisson, it'd be t equals 0 up to infinity for Poisson, up to n for binomial. Probability x equals x times t to the power of x. So that's our original definition. And so we end up with, starting at 1, a quarter t, and then plus 3/4 times a quarter t squared plus 3/4 times a quarter t cubed plus 3/4 cubed times a quarter t to the power 4, etc. So I can pull a quarter t out of all of those terms. And then I end up with 1 plus 3/4 t. Sorry, I just forgot I'd taken the t out. Mikey, I'm recording. I'm recording. Plus 3/4 t squared plus 3/4 t cubed plus, and so on. And then we're in this case again where we've got an arithmetic series here. So to get from one term to the next, you're timesing by 3/4 t. And so summing that, I might need another board. So coming back into here, sorry, A is 1 and R is 3/4 t. And so the probability generating function of t is going to equal 1/4 t lots of A over 1 minus R. And then rewriting that, the 1/4 t would go on top. It's a bit unusual to leave a fraction in a fraction, but it kind of makes sense to for this one because P is 1/4 and Q is 3/4. But that proves that result. And then we can generalise that. I'll go back to my other board. We were right, yeah. And so generalising that, if X is GOP, then the probability generating function for X is equal to PT over 1 minus, you could just write QT. I think the formula book has 1 minus P, so I just keep that consistent with the formula book. But that's your result for the probability generating function of a geometric distribution. And you can see that essentially we've got the same thing. I don't know if you can see that actually, but you've got the same thing here as here.